Hi, I'm Samir. I'm going to be talking about what the last talk sort of covered, which was the LIME algorithm. Uh, I was responsible with a bunch of people, and I'll sort of tell you about why we looked at that algorithm, why did we create it, uh, how we sort of got it working, but also since we've released LIME, some couple of other research ideas that we've been exploring more recently. Okay. So my first slide is sort of obligatory. Everyone kind of knows machine learning is everywhere. It started off being sort of somewhere out in the cloud that you didn't really know was happening. Email would just go to spam and you didn't care. But soon it's sort of in the last maybe five to a decade, it's become very sort of public in terms of people talking about machine learning, on Jeopardy, AlphaGo, all of these examples. Machine learning is pretty much, now that it's playing games for us, it's dictating what we do with our time by telling us what to watch. Machine learning is on our phones, it's in our houses, it's going to be in our cars, right? So it's pretty much everywhere. So it's worth kind of thinking about what exactly is going on when you use machine learning. So I'm going to start with a simple example of trying to figure out, given an animal that you find somewhere, whether you should adopt it or not. So basically, we're going to be training a classifier that tries to distinguish between a wolf and a husky, where wolf is not something you can adopt even if you would like to. So the idea here is you take an image of the animal that you find, you give it to your classifier, and it should hopefully tell you that this is a wolf. Don't adopt it. On the other hand, if you see something like this, it looks a lot like wolf. I wouldn't be able to tell you necessarily it's not. But the machine learning hopefully is smart enough that it should be able to tell us that, right? And now the cool thing is that machine learning has gotten to a stage where if you have a bunch of these images tagged, just like sort of the last example showed, you can sort of set this whole pipeline up in a matter of maybe a couple of hours and get a really good classifier. So this is what the classifier might do on this data, where it gets most of them correct. It makes actually only one mistake, which is sort of much better than what I would do, for example. I don't want to speak more generally. But wolves and huskies are difficult to tell apart, so it seems to be doing something pretty cool. But this is just a simple example of what you can do if you just have a few data points. Let's take a look at sort of more state-of-the-art research and what that looks like. This is an example of a more complex task known as visual question answering. And the idea here is that you're given an image, even if it's a really strange image of a woman with bananas strapped to her face, who looks like is taller than 7 feet from what I can tell. But anyway, you give this image to a machine learning agent, and it has never seen this image before. And then you can ask it questions like, is there a mustache in this picture? And now you might argue yes or no. The machine learning says yes. And that's kind of interesting because it has never seen a mustache made of bananas, but seems to be interpreting a more abstract concept of what a mustache is, right? This is still a binary yes or no, so you might not be very impressed. In fact, you can ask it any question like, what is the mustache made of? And the answer is not just yes or no anymore. It's a word out of whatever, 10,000 to 50,000 possible words. It picks banana, which is, again, it has never seen a mustache made of banana before. So all of this seems pretty interesting and impressive. But the problem is that essentially, both of these algorithms that I showed you are black boxes. We don't really know exactly what's happening in there. We can look at a few examples and convince ourselves that it's doing well. But we don't really know whether we can actually trust it, right? Whether we can take that model and actually deploy it in the wild. What will it do? Like, can we trust it that it'll always do the right thing? It's not clear. Specifically, from a developer point of view, if you're building machine learning models, you want to deploy it only if you can predict what it's going to do. Because if you can't predict what it's going to do, then it's a sort of risky proposition. But you also want to know how to improve that model. And if it's a black box, doing any of these three things is a bit problematic. Right? So for example, if we go back to this example that I showed you, where the machine learning classifier was making only one mistake, I'll tell you how we sort of came to this conclusion, but it turns out that this machine learning classifier is basically detecting snow. Right? Every time it sees snow, it predicts wolf. Every time it doesn't see snow, it predicts husky. Right? Now, clearly, there's some correlation, and it happened to get pretty decent accuracy on this data set. But if you were to take this classifier and try to apply it in the real world, you will get cases like this, right? This is a real news story. Obviously, they didn't use machine learning, but the point is, yeah, it'll in the real world, it'll make a mistake because it's only looking for snow, not looking for actual animal. But that was a classifier that I constructed for you, so sure, we can set these things up. The problem is that if you've played with machine learning, you would have seen some version of this pretty much any time. Even with state-of-the-art methods, you can sort of take a look at what would happen, and you would realize that a lot of them are quite brittle. So for example, I showed you this case of asking what is the mustache made of, and it said banana, and that seems quite impressive. We were playing around with a bunch of different questions. So we asked, what are the eyes made of? And it said bananas. That was a bit disappointing because now it's not clear. Earlier we thought, OK, it's learning what a mustache is and figuring out it's made of bananas. Now we are not so sure. So we asked a few more questions like what? And it said banana. We said, what is? Question mark, and it said banana. Right? Clearly now it suddenly doesn't seem like a super intelligent agent that's going to take over the world and replace humans. But that's not what we thought initially, right? And this sort of happens all the time. This is sort of more synthetic examples. I can give you another one that sort of corresponds to how research takes place. This is an example of email classification. It was actually Usenet posts, for those people who remember what Usenet is. And you had to classify each post into some category. In this case, you had to classify it into whether it's talking about atheism or whether it's talking about Christianity. Okay? And it turns out that we trained this classifier that was getting 95% accuracy on this task, so we were pretty happy. But this is one where it was actually making a mistake. It seems to heavily think that this Usenet post is about atheism, where, I mean, if you take a quick look, it's clearly not, right? And so now the question arises, OK, it's getting 95% accuracy. How can it get something which is so obvious, so wrong? Right? Here's sort of another example that I can imagine would be the case where, for example, if you're applying for a loan and you give the information to some crazy neural network, it might reject your application. And you might want to know why the application got rejected. So this is not from a machine learning designer point of view. This is purely from a user point of view. If you just look at neural networks right now, most of them can basically spit out a bunch of numbers and say, that's what I think, why I think I rejected your application. And clearly, that's not very useful. Right? So a natural question is, how did we end up getting here? And I'm going to give a real quick sort of walkthrough of why machine learning is the way it is right now. Right? So initially, machine learning was something that was working on very simple data. In this case, let's assume there were only 2 dimensions. And so you would need to classify a point in 2 dimensions. You would gather some data set that might look like this. And you will try to figure out, given this, that there should be maybe a line that should divide them. And what is nice is a line in 2 dimensions is an equation you can write down. And you can actually understand what's happening. You can look at the coefficients. And you can say things like one of the dimensions has a higher effect than the other one. Right? Similarly, you can think about the data getting a little bit more complex. in which case you can't just do one line. Maybe you need 2 lines to split this thing up. And at this point, it's looking more like a nested if-then-else statement, where each line is sort of conditioned on the other one. Right? And again, this is when its data is simple and the dimensions are small, it's something you can sort of look at the structure and you could say, yeah, x2 is less relevant than x1 and blah, blah, blah. Right? Why looking at this thing is important is because it sort of helps us address all of these problems we had earlier. We know whether we can trust a model or not if this structure sort of matches our intuitions. We can predict what it's going to do because we know the structure. So the structure tells us exactly what the model is going to do. We know where it's going to make mistakes and where it's not. And finally, if we want to improve it, we can look at parts of the structure that seem wrong and sort of focus our attention in those parts. Now, what changed was this arrival of big data, where suddenly the applications of machine learning really exploded. And it's still exploding, and it's still sort of growing exponentially. You had language, you had economics, you had biomedicine, banking, finance, retail industry, commercial stuff, humanities, and just sort of basic sciences as well. Just lots and lots of applications, right? Now, applications by themselves is not a problem. The problem was that with this big data, the underlying data became quite complex. So for example, we were looking at just 2-dimensional cases. Instead of a line or a bunch of lines, now the surfaces look a lot more like this. Now you can imagine writing an equation for this. It'll be some really high polynomial equation. And now suddenly you can't just look at the coefficients and understand what's going on, right? Because it's a really crazy surface. And this is a curve that we just drew up. But in fact, this is actually the case. So for example, this is an example that McKinsey released. You can see all of these contours, and they basically define on some 2 variables that they won't tell us the names of, sort of what is important and what is not. And the green curve is what the traditional machine learning would do, sort of a simple statistical curve. But now, to actually capture the complexity in the data, you need a machine learning model that has these lots of bumps and things like that, which basically means lots of coefficients and stuff that we can't understand, right? Now, the problem is not only the fact that the sort of surface gets more complex. The other problem is that the number of dimensions also exploded, right? So instead of just using any 2 sort of features that might be relevant, so for example, looking at savings and income that might be relevant for a loan, you suddenly had a bunch of other things that people would throw into the model, right? What that means is that the number of dimensions is not just 2, which was never the case really, but it's not just 10 or hundreds anymore. It ends up going into thousands, tens of hundreds of thousands, and easily into millions, right? So now if you think about what's happening, we have this really complicated curve that even in 2 dimensions, we can't really understand what it's doing. And we have these billions of dimensions, so we can't even properly visualize 4 dimensions. Imagine trying to visualize millions of dimensions. And so the complexity level is basically so high that machine learning becomes a black box. Okay, so now that we know machine learning is a black box, let's sort of think about what it means for interpretability. Right? So what I'm going to do is sort of give you a cartoon example of what interpretability of machine learning models look like compared to their accuracy on these complex data sets. The simple models that I showed earlier would sort of lie somewhere there, right? They're highly interpretable, but incredibly inaccurate, so kind of useless for our task. You can sort of make each of these more complicated and get them to be more accurate, but you're losing interpretability. So for example, instead of a simple tree structure, it becomes this nested kind of forest structure that's, again, uninterpretable, and there's no way we can understand what's happening. So there has been a lot of research on trying to create interpretable machine learning models. And I think that's really exciting. And I'm hoping to see some really cool stuff come out of there. And they've given us a lot of information about what humans find interpretable. But at the risk of generalization, I'm just going to say that a lot of them don't sort of fit the real world use case, right? And so deep learning kind of came along and said, OK, the data is really complex. There are lots of dimensions. Let's just put the most complex algorithm on top of it and just sort of ignore the interpretability part. Right? So there's a bunch of methods that just focus on accuracy, trying to get as much as possible. And for many tasks, as we increasingly became aware of, in terms of accuracy, they sometimes beat humans. Right? The problem now is that it's too complex. So all of these things that we were doing by looking at the structure, they kind of go away. Right? So with this, we sort of started looking at, OK, can we actually create an algorithm, which we call the Lime algorithm, to explain or to sort of simplify and explain why these models are making the predictions they do. So the idea here is you're given a data point, and you have some machine learning model that makes a prediction or makes some decision for that data point. What we're going to do is we're not going to make any assumptions about the actual algorithm. Basically, instead of looking at what the structure is, we're going to just forget about it and treat it like a black box. Right? It's just some function where you give it a data point, it gives you a prediction. Why did we do that? Well, firstly, we wanted to support all existing sort of algorithms. But in some sense, it also makes our method future-proof, right? Even if somebody comes up with a really new algorithm tomorrow, since we are treating it as a black box, we can still sort of work off of it. So the idea here is that when you think of this curve that I showed you about accuracy versus interpretability trade-off, we are not trying to add more points to this plot, because I think people are getting really accurate models. We don't want to trade them off. But in some sense, we just want to move any of these models to the interpretability side without any loss in accuracy. Right? So we're going to be taking trained classifiers and then trying to explain on a post hoc basis. So here's what an explanation actually looks like. I gave you this example of this post being tagged atheism. The idea here is that we figure out for each word or for each label which words are most important for the label. Right? So we'll have one column for atheism, one column for Christianity. We look at which is the most important word. Turns out it's Christianity. And it also turns out that the classifier thinks it's most useful for tagging the Usenet post Christianity. So that's great. That's sort of, if somebody's saying Christianity, Christianity, that means they're most likely talking about Christianity. And that sort of makes sense. The second word that seems to be important is the word posting, which happens to be in the header. And the model thinks that that really indicates atheism. In fact, the second word is the word host, which also appears in this header, and that's also indicative of atheism. Even the third word, which is the name of the sender, Keith, it turns out in this data set, Keith is highly correlated with being being an atheist. Keith Richards especially, no surprise there. And that's also very indicative of atheism, right? And then there are some sort of lower important words, like answer and is, that seem to be one or the other with some low weight, right? So now suddenly we had no idea earlier why the classifier was getting this wrong. Now, not only do we have an idea, but we kind of know what the problem is. The problem is we wanted the classifier to only look at the body, and we let everything else in, assuming that it wouldn't cause a problem. But clearly, having the header in there causes a huge problem, right? And now this is not some mistake that we made. A lot of papers have been written on this data set just sort of treating it like machine learners like to do. Oh, it's just a bunch of features. Oh, I got 95% accuracy. Turns out it was just picking up on these kind of signals that happen to be in the test set as well, right? So it's not really a meaningful classifier that now you can turn it into a Gmail plugin and add it to your Chrome browser, right? So the idea here behind Lime is, again, overall describing their behavior is too complicated. This curve, the surface is really complicated. There are too many dimensions. We are going to instead explain a single data point by only looking at what's happening around that data point. So instead of thinking about the whole curve, we're just going to find a part that is most important and sort of zoom in. And then look at some part that's more important and zoom in. And we're going to keep zooming in till we can easily find a simple model to fit the local region around that data point. So in this case, we've zoomed enough that now a line is a good explanation for what's happening for this data instance. Right? And so that line now becomes the explanation. It's the explanation for the classifier's behavior for this specific data point. We're not saying anything about what's outside this data point. Just for this specific data point, this is the behavior. So we can apply it to a bunch of sort of neural networks. We took Google's object detector, the Inception Net one, and we gave it a pretty strange image of a dog playing a guitar. And it predicted that it was an electric guitar with a pretty high probability. And we were able to find out which part of the image was most responsible for predicting it to be an electric guitar. Turns out it seems to be the way the dog is holding the neck and just the neck itself that makes the neural network think that this is an electric guitar. It also thinks it's an acoustic guitar with a slightly lower probability, and turns out it's because of the body of the guitar that it thinks that it's an acoustic guitar. It also thinks it's a Labrador, and turns out it's looking at the face, so clearly it's a Labrador. It's also kind of looking for maybe the leg or something like that to sort of figure out that this is a Labrador. Right? So this was a pretty good classifier, I would say. Let's go back to one of the bad classifiers that we had created earlier. I showed you this example. Let's just forget about the snow fact that I told you, and let's look at what the explanations look like when we ran Lime on this. These are what the examples that Lime produces look like. You can see for each image, there's the Lime explanation, where a lot of the image is gray, especially when you look at the ones where we predict it to be a wolf. You'll see that the explanation doesn't have the wolf part in it at all, right? So look at the first one, only the snow on the ground kind of shows up. Right? Even the last one, the neural network is completely ignoring the wolf. It's just looking at what's on the ground. Here also just looking at what's on the ground. And here also, it's just looking at what's on the ground, right? So to classify which animal it is, it's not even looking at the animal. And so if you think about what we've done, we've actually just built a great snow detector, and the explanations are telling us that. Sorry. So we actually ran a lot of experiments. I'm not going to go through all of them, but some of the things you can do with these explanations is you can take one classifier and take another classifier, and they may be different in sort of any respect. And you can obviously compare them using a bunch of metrics or just using your intuition. All of them have their positives and negatives. The intuition one is mostly negative. We thought maybe explanations can be useful to compare two models as well. The idea here is that if we know that this is a wolf, if we look at an explanation like this, we should think, okay, this is maybe not a good classifier. If we get an explanation that looks like this, we should think, okay, yeah, that seems to be like a good classifier because it's actually looking at the snout, it's looking at the ears, it's looking at the fur on the back, as opposed to just looking on the floor. And so that way we can call this a bad classifier and call this other one a good classifier. We could also think about doing this for the text classification example I had. This is an example of a bad explanation. And so by looking at the explanation, you can say, okay, this doesn't make sense. I won't trust this model. This is an example for the same task. It's a different email and a different classifier. But here, we've sort of colored it differently. But the words that appear here that seem to be indicative of the labels seem to be correct, right? Atheists like to talk a lot about morality. Christians like to talk a lot about themselves. Both of them like to talk about God. It turns out Christians use capital G when they refer to God, and atheists use small g, right? So now it seems to be capturing not just obvious things, but even things that are slightly surprising, but also make sense in hindsight. And so this would be a good classifier, right? So that's just an example of how we can use LIME explanations. I do want to cover some of the more recent work we have done, sort of trying to extend and address some of the flaws we found with LIME. It's going to be work on trying to use counterfactuals and counter examples as a way to explain. Okay. So the idea here is that we're going to assume that the users can understand what a machine learning model is doing only if they can predict what the model would do when it's deployed, right? So if you understand something, you would be able to predict what it would do on completely new data. So we can define sort of a precision and a coverage measure of what this predicting looks like. So if a human can predict correctly, whenever it makes a guess, they're correct, that would be a high precision user. And coverage is just how many times they're offering to make a guess. Right? And the idea here is that the precision, when you're trying to predict someone's behavior or machine learning's behavior, prediction is much, much more important because if you have high coverage but low precision, it means you like to make a lot of guesses, but you're completely wrong in what you think the classifier would do, right? So it's better to be not confident about making a guess rather than be confident and be completely wrong, right? So now if we think about what LIME does and why it is not really good for predicting what the model would do, what it's actually doing, for example, if a review says this movie is not bad, it sort of gives you an explanation where it tells you how much important each word is. So in this case, it's going to say bad is a negative word, but not is a positive word, because not is making this a positive prediction. So if you think about what's going on in the surface, there is some line that LIME corresponds to, right? On the other hand, if you say this movie is not very good, in this case, the word not acts as a negative, right? Same word, but in this part, for this example, not is actually flipping it from a sort of positive sentiment to a more negative sentiment. And so if you think about the line that LIME corresponds to, that will have a different direction because the coefficients of not are sort of opposite, right? Now the problem is, if you're given a new example, how do you know which of these two explanations to use? If I give you another example that has the word not in it, which one would you use? Specifically, if you think about what the line is doing, it's going to be wrong in a certain area completely. Similarly, some explanations are better than the other, and LIME is not actually telling you that. The other problem is that the coverage is not clear. So if you have some region here that's pretty close to the original instance, we don't know whether LIME explanation applies or not. So to address this problem, we introduced these anchor kind of explanations, which are going to be sort of precise counterfactuals for what the classifier is doing. So let's look at what an example would be. Anchors are extremely easy to understand. For example, the anchor for this, for the first example, would be the phrase not bad. So it would say if not appears and bad appears, then you predict positive. Otherwise, I don't know what's going to happen. It's only a sufficient condition, right? And the way we generate this is we sort of create a bunch of fake sentences. The audio is not bad, the novel is not bad, the footage is not bad, sort of. If all of them are positive, that's when we come up with the explanation. So anchors now start looking like a square instead of a line because it's a rule. It's not a set of coefficients. Right? For this other example, the anchor looks like another square, where it means that if it's not good, then you say it's a negative sentiment. And these are examples of sentences that sort of fall under this anchor. Okay. Now, what's really nice is it's really clear about what the coverage is, because if the condition of the rule applies, you're set. If it doesn't apply, you're not set, right? Secondly, we are sort of using probabilistic guarantees when we are computing it. So if the users just blindly follow these anchors, they're actually going to be correct almost all of the time. Right? That's also good. So I'll just show you some examples of what these anchor explanations look like. So for example, this is a salary prediction task where you're given a bunch of attributes about a person, and you're supposed to guess whether their salary is greater than 50K or not. This is, I think, a few decades old, so yeah, take that into account. And what line gives you here is something like this, right? It tells you that the capital gain, if you have it 0, it indicates your salary should be less. If you're married, it should be more. And it's kind of giving you this sort of directions about which ones are important. But what the anchor gives you is something very, very clear and precise. It says if the education is less than high school, this classifier will almost always predict the salary to be less than 50K. Right? Something very precise, very clear, something anybody can just understand. Right? We can also apply this to this example we had way earlier of this image, and we asked the question, what is the mustache made of? And it said banana. Some of you might have noticed that the word what is bolded here. That just means that the anchor was just the word what. Right? If the word what appears in the sentence, the answer was banana. That's what the anchor automatically told us. And it did so by creating a bunch of different questions, like what is the ground made of, what is the bed made of, what is this the picture of, and the answer by the machine learning classifier was always banana. Here's a different question, how many bananas are in the picture? Answer is 2, it gets that right, but it's only looking at the word many. So you can create a bunch of questions like how many are in the picture, how many people are in the picture, how many zebras are in the picture, and it's just always going to say 2 because it's just looking for the word many and giving it the answer 2. Right? In the end, I want to give you a few other examples of more complex tasks we've been working with. So this is sort of a translation, machine translation model, where we have English to Portuguese translation. And we wanted to know why does the word esta appear in the translation. And turns out the word esta appears here because of this is, which is the literal translation of esta, but also because of the word question. And now if you know Spanish or Portuguese, you would know that this is the case because esta is actually feminine, and so is question. So question dictates whether esta would appear or not. If you replace question with something else, like a problem, then it would be este, right? In fact, if there's a different sentence that says this is what we must address, then it's sort of an unresolved reference, and it's a completely different word that gets used in Portuguese, right? So, yeah. With that, I think I'm going to close my talk. Hopefully, you guys understand that explanations are important because you want to be able to trust, you want to be able to predict, and you want to be able to improve the models. And we've been looking at these sort of family of model agnostic explanations. And hopefully, that is a good direction to go in. And it sort of tries to solve at some of these problems. Before I close, I want to thank a bunch of my collaborators, including Marco and Carlos, who were responsible for the Lime stuff, and some of the most of the Anchor stuff, and some of my PhD students who are working on these directions as well. Thank you. Yeah.